Alright guys, welcome to lesson 7 of unit 7. We're moving into our last bit of territory here, which is talking about volumes of solids. So we've talked about area, but now we're going to move into three-dimensional shapes and talk about how integration can help us with finding volumes of solid figures. So we're going to spend the next 2 lessons on finding volumes of solids with known cross-sections. So what that means is like, for instance, like if I were to give you guys a shape of a rectangular prism. This is not drawn very good. Kind of hard to draw things here. Well, if you were to cut this rectangular prism down the middle, you would see a square, and that's a common geometric shape. And so when there's a common geometric shape as a cross section, then we can easily find the volume using integration, and that's what we're going for here today. So let's go ahead and jump into helping you develop the idea, and then I'm going to give you the steps we're going to follow, and then we're going to go ahead and do a couple of example problems. All right, now first of all, I've got a graph here. You guys don't need to write this, but I would highly encourage you guys to watch this video and make sure you understand the ideas I'm developing here, because this is what's going to help all the things we're doing after this make sense. But you don't really need to write anything here just yet, okay? So let's say that this red line up here represents f of x, and we'll say that the blue line underneath of it represents g of x, okay? Well, let's say I wanted to find a function that represents the distance between these two functions at any given point. So in other words, at this point here, how far apart are these functions at this particular x value? Like let's say at 0.4. How far apart are the functions? Or in other words, how long is this purple line? Because that would be the distance between them. Well, the way that you find the distance between these functions is by looking at the y value of one and looking at the y value of the other and subtracting them. That'll tell you how long it is, right? So it's really just going to be the function that's on the top minus the function that's on the bottom. And that represents the distance between those two curves, right? And that's a function. That distance is a functional distance because it changes depending on where I decide to move my x value. And move it up here. Now it's something else. So now I've got this function here, f of x minus g of x, which always represents the distance between these functions for any given value of x. So if I were to plug in, like right here, about 0.8 for x, then that'll tell me the distance between those lines. Or if I were to plug in 0.2 for x, this function here will still tell me the distance between those functions. So this is what we'll call the distance function, the distance between those two functions. And the way you do it is just do the function on top minus the function on the bottom. Now, that should sound a little bit familiar based on the past few lessons we've been doing. We've been subtracting top and bottom for the past couple lessons, haven't we? Right? Well, it just so happens that we could find a whole bunch of these things, actually. Find a whole bunch of these distances and put them all in there. So there's a whole bunch of distances here between these two functions. In fact, I could find quite a few of them. But as you can see, the more I find, the more it just begins to become the area, doesn't it? And as you guys know, the area between two curves is just taking the integral of the top minus the bottom from your starting x value to your ending x value, which in this case is 1. Okay, so this is another way of thinking about what we've been doing already for the past few lessons. Top minus bottom, integrated from beginning to end. But the new thought here is that this function right here, top minus bottom, what that really is that's a function that represents the distance between these two functions. And so when you integrate that distance, from 0 to 1. In other words, if you find an infinite number of them and add them all together, you get the area under the curve, right? All right, so now it's time to blow your mind a little bit and get you to expand your thinking. So I'm about ready to turn this two-dimensional picture into a three-dimensional picture. It's two-dimensional because we have a height and a base, right? But I'm going to rotate this, and it's going to instantly become a three-dimensional picture. Whoa, what just happened there, Mr. Bailey? Mind blown. All right, so this is actually a three-dimensional space that we're working on here now, right? So now this little distance right here, this purple line, that's still f of x minus g of x. That's still that distance. So right now, though, I don't want to think of that as an integral. We'll come back to that in a second. For now, let's just remember that that purple line is the distance between those two functions, which is still f of x minus g of x, even though I'm looking at this now as a three-dimensional picture. Now here I want to do something else that is a little wild here. I want to put a square here on top of this line so that this line is the base of the square, and the square will also have to have the same height as the base. So I'm going to put a square right there, just like that. So now I've got a square with a base that is equal to the distance between these curves. So in other words, the base of this square is f minus g, right? Now, since it's a square, if the base is f minus g, then so is the height. So this distance right here is also f minus g. And how do you find the area of a square? Don't you do base times height? So if I take the distance between my red function and my blue function, which is f of x minus g of x, and then I square it or multiply it by itself, that tells me the area of a square whose base is equal to that distance. And we can move that around. So now I've got a new function. This new function isn't just a function that tells me the distance between the two curves now. Now this new function, if I square it, is a function that tells me the area of a square on the three-dimensional picture that we see here. So sometimes it could be a really small square, sometimes it could be a really big square, but it could be a lot of places. But what happens then if we do what we did on the last one? What happens if I put a whole bunch of these squares on here at once? More. How about some more? Well, now we're integrating, aren't we? We're adding a whole bunch of squares on there. Now, what if I were to add an infinite number of them? Well, that becomes a solid shape now, doesn't it? So I just turned that two-dimensional picture into a three-dimensional picture by putting a square on top of that length and then putting squares everywhere and integrating. It's an interesting looking shape, isn't it? Well, I shouldn't have integrated, I'm saying adding. But that is integrating, right? So we're integrating from 0 to 1. Now, if you look at this as a two-dimensional picture again, it just looks like the area between the curves, right? Which is the integral from 0 to 1. But in reality, since I'm squaring it, we're thinking of that as a two-dimensional picture with a bunch of squares added together instead of lines, which gives me a three-dimensional image here. Okay? And so that's the idea. Now, there's no rule that says that it has to be squares, though. Now, but if I change my shape, the area formula will have to be different. So I'm going to go ahead and get rid of this for now because it's going to be different, but the idea will be the same. So there's no rule that says it always has to be a square. I could put a triangle up there instead. See that? I can make the base, the distance between these two curves, I can make that the base of an equilateral triangle, for instance. And once again, I can put an infinite number of those on there. And I get a different looking three-dimensional shape as a result of that. Kind of looks like a fish. All right? Or we could do semicircles. Get rid of those triangles. So now we're looking at semicircles being stacked on there instead. And that'll give me a slightly different shape. A little bit smooth. All right? So that's the idea of today. Today, we're going to follow a three-step process. Step one is we're going to think of this as a two-dimensional picture, first of all. And we're going to define the distance function between these two functions as f minus g. And what that f minus g is going to represent is the base of our shape, our solid. And then what we're going to do is we're going to do some geometry with that base. Like, let's go back to a square, because that one's a little bit more familiar to our thinking right now. We're going to do some geometry with that shape. So if I want to put a square on there, we're going to square that base to find the area of the square, and then we're going to integrate it from the starting x value to the ending x value. And when I do that, it adds an infinite number of these little squares together, and you end up with a solid. And you could do the same thing with other shapes, triangles and semicircles. You just have to know how to turn the base into an area formula. For squares, it's really easy. You just square it. For semicircles and equilateral triangles, it could be a little bit trickier. But the idea is the same. So it's a three-step process. Step one, find the distance between the curves. Step two, turn that into an area formula of a shape. Step three, integrate, and you'll have a volume of a solid. Okay, so here's our steps, and this is something I would encourage you guys to write down. So the first thing you do is write an equation that represents the base. Now, what do I mean by the base? I mean the base of the shape that we're going to be stacking on top of our curve. So remember how we had f minus g? The base was the distance between them. So that's top function minus bottom function. And I call it the base once again because when you rotate this, this becomes the base of the shape that you're going to be stacking on top of your region. All right, so that's the first one. Write an equation representing the base. It's the top function minus the bottom function. Now, once again, just like when you're finding the area, if you want to just avoid the whole question of which one's on top and bottom, you could just put this in absolute value bars, and that will correct the issue for you. Even if you accidentally put them in there backwards, it'll still work. So this is really the safest way to do it, is put absolute value bars on. Next, you're going to use geometry to write the area of the cross section. The cross section is what you get when you think of this as a three-dimensional figure, right? Like there's my square stacked on top of the three-dimensional surface. So what would you have to do to your base here, which is usually just going to be f minus g? What would you have to do to that base to get the area? Well, it depends on the shape. We saw that if it's a square, you just square the base. But we're going to look at some other shapes, and this is how those will be handled. And I'll explain more how we get these formulas a little bit later. Rectangles can be slightly different every time, so we'll see that later as well. But let's review. So write a formula representing the base, or the distance between those two curves, top minus bottom absolute value. Then use geometry to write the area of the cross section, and it will have to involve the base somehow. And then third, you're going to integrate. And after you've done that, voila, you've got your volume solid. You've got the volume of the solid that they're asking for. And so we're going to be using those same three steps. And this is going to be a 2-day lesson. We're just going to look at and the whole reason for it is really just because of the number of examples I want to go through. I want to go through a variety of problems to show you different things that can occur along the way, right? So we're going to get through half of the problems today. We'll get through the other half next time. Okay, so let's go ahead and take a look at our first example. Now, for teaching purposes, I'm going to draw these pictures. And I think that it would be good for you guys to do that. But you actually don't need to draw the pictures to do these problems. But it can be a little bit helpful because the more you can visualize what you're actually doing, the better you're going to be able to set up your problems. Okay? So let's go ahead and begin here. So what I will give you, though, on every problem is at least a picture of the original shape represented by this function here. So now I want to find the volume of a solid. And the bottom of this solid is this semicircle here represented by this equation. And the cross sections are going to be squares that are going to be perpendicular to the x-axis. Okay, so now the distance that I want to find is like the distance from here to here. These are my bases. So the distance between the curve and the x-axis. Okay, now that length is really just the y value of this function. So in other words, if it's just the y value, then that is the base. Now, when I was doing my example, we were looking at area between two curves. But if you're just looking at the area between a curve and the x-axis, then that base length will just be the function itself. So my base is that function. So that's step one, is to identify what your base is, and we've got that done. Now, I'm going to view this three-dimensionally. So if I were to take this graph and I were to lay it down flat, it would look something like this, right? And what I want to do is I want to stack squares on top of it like that. You guys are like amazed at Mr. Bailey's art skills now, aren't you? Now, each of these squares has a base that's equal to this function. And since it's a square, the height is also that base. And so since we're dealing with the area of a square, because that's what it's asking for, square, the area of a square, so I'll put A with a little S right there, so I know we're talking about squares. Matter of fact, I'll put SQ. The area of a square is going to be the base squared, right? So then in this case, the area of one of those squares is going to be the square root of 9 minus x squared squared. Now step 3, which I'll do in a different color here, is to integrate this. That means I'm going to stack an infinite number of squares on here and add them all up. And we're adding from what to what? From this point to this point, which on this graph over here, you guys can see is -3 to +3. So we're integrating from -3 to +3. And that's how you will find the area of that function. Now, at this point, I would just type this into a graphing calculator to get the answer. Okay? Now, I'm making this lesson at home, so unfortunately, I cannot display my graphing calculator. But here's how I would do it. I would go to the y equals, and where it says y1, I would type in this function, 9 minus x squared. And then I'd go back to the home menu, and then I would type in this y1 squared, where y1 represents this little piece right here. And then I would push enter. So I'll tell you what you should get as a result. If you go ahead and work that out, you should get a final answer of, let's see, 36. Okay? So once again, the basic steps are identify your base, which in this case, since we're just going from the curve to the x-axis, is just the function itself, the y value, or the height, which is that equation there. Then, since we're doing squares, it's the base squared, which gives you the area of one of these squares here. And then if we integrate from -3 to 3 in step 3, that will tell me the volume of the shape that would end up looking something like this at the end. Okay, and that's the volume of that strange looking shape there, which is about 36 cubic units. We don't know what the units are, but since we're doing volume, those are cubic units. And the way you put it into your calculator is you're going to type the base function in as y1, and then you're going to go back to your home screen and enter the integral from -3 to 3 of y1 squared instead of the function squared. You could just type this function in on your home screen. The issue is that I just find that it's a little bit easier to have it stored, and it leads to less typo errors if you do it this way. Okay, so what I'd like you guys to do now is I'd like you to go to your not your student practice, I'd like you to go to your homework worksheet, and I would like you guys to do number 1. So pause the video here and see if you guys can calculate the area of this shape. And when you're all done and you unpause the video, I will show you the solution. All right, so here is the answer to your first homework problem. So this is the base of the solid, right? This is the two-dimensional view. And if you were to lay it down flat, it would look something like this, right? And we are laying down squares that are perpendicular to the x-axis. They look like that. The base is the distance from here to here, which is just this function right here. And then since we're stacking squares, we're just going to square the base of that shape, and we're integrating from -4 to +4. Putting all that into your calculator, you should be getting 68.267. You might be wondering what's up with this y equals 0. That's just another way of saying the x-axis, which is just we're integrating from the parabola to the x-axis. Same thing as last time, not a big deal. Let's move on to example 2. Now I just want you guys to know it's a convenience that you can see where these graphs are crossing. So I'm giving you guys an added bonus of being able to see the graph. And actually, I've found that a lot of times on the AP exam, in fact, every time I can think of, they always do give you a picture. But you want to know what they don't always give you is they don't give you any numbers here on the axes. So sometimes you don't know where these are crossing, and you need to find that yourself. Now, we've learned a few ways to do that. We've learned to do it on the calculator. You could also find where they're crossing by just setting these things equal to each other and solving the equation. Now, I'm not going to be doing that today because it takes too much time and we're learning a new concept anyway. But it is very possible, and I might even toss 1 or 2 of those at you in the homework or on a study guide or something, because you do need to know how to do that. All right, but that's an old skill, and I don't want to focus on that right now. So now example 2, instead of just having one curve going to the x-axis, we're going to be doing 2 curves in the area between them. So in this case, and that's kind of like the one I did on the opener today, we have 2 functions. Let's call this one y1 and we'll call this one y2. Now, clearly y1 is a linear function, so that's going to be this straight line right here. And y2 is the quadratic, and so that's the one that's going to look like this right here. That's the parabola. Now, once again, you usually have to find where they cross mathematically, but in this case, we could see where they're crossing. We want to start at x equals 2, and we want to stop at x equals 5, right? Now, I want to find the distance between these 2 curves, so from here to here. Now, how do I find the distance between 2 curves? Well, you do the function on top, which is y2, minus the function on bottom, which is y1, and that's the distance between those curves. Now I want to view this three-dimensionally, so I'm going to lay this graph down. I'm going to do my best to sketch this. I don't know how I'll do, but we'll see. So there's the linear function. And then my parabola will look something across here, up here, and here. So maybe all right. So there it is, and we're finding the distance between these 2 curves here, and we're stacking squares on it again that look like that, right? So if this represents the base. So when you have 2 functions and you're finding cross sections that are on top of the area between 2 curves, then the base is no longer just one function, but now it's the difference of those 2 functions. And like I said, sometimes you can't tell which one's on the top and bottom, but it really doesn't matter if you don't know, if you're using a calculator, because just to be safe, if you just put absolute value bars on there, it doesn't matter which one's on top and bottom. We've already talked about why that is as well. Okay, so now that's the distance between there. And if I were to square that value, that's going to tell me the area of the square that I'm stacking on top of that with a base of that distance. And then I want to integrate to find the volume of the shape that would result if I added together an infinite number of such squares. Okay, and that I'm going from 2 to 5. And then once again, we're just going to do this on our calculator. So once again, I can't show it unfortunately because I'm at home and I can't display my graphing calculator, but I'm going to be calling this one Y1, and so I'm going to enter that into the Y1 slot on my calculator. I'm going to be calling this one Y2, so I'm going to be entering that into the Y2 slot on my calculator. And then this is what I'm going to type in on my home screen. Okay, now absolute value would be nice to have in there. Now, we don't really need it because I do know which one's on top, but you know, it's a good practice. Just in case you screw up, if you always do it, you just won't make the mistake. So I'm going to include the absolute value. And here's the answer if you do go ahead and plug that stuff into your calculator. So there you have it. So same difference as last time. The only difference is that I've got the wrong picture up here. Let me bring back the original. Here we go. Sorry, so 8.1. So it's the same way of doing it last time. It's just that instead of having a single function here, which is what you do when you have just a curve between that and the x-axis, when you have two separate functions and you're finding the equation between those, then you subtract them with absolute value bars, but you still do the squaring and limits there. All right, so let me give you guys yours. That would be this next one here, number 2. Go ahead and pause the video here and see if you guys can find the volume of a three-dimensional shape with this as its base, and it has square cross sections that are perpendicular to the x-axis. Right? When you unpause it, you'll see the solution. All right, so we are finding the distance between y equals 4, which is y1 here, and x squared over 9, which is this u shape. So the distance between these two curves, represented by this vertical line, which is going to be the base of our shape that we're stacking on top of it, is y1 minus y2. y1 comes first because it's on top, y2 comes second because it's on the bottom. But if you put absolute value bars, it doesn't really matter if you got that right or not. And a matter of fact, since we're squaring it, it doesn't matter anyway because squares also cancel out negative. But just for good practice, I'm going to include it. We're going to be integrating. Well, actually, we're going to square it now because, right, we're stacking squares on it. So if you want to think of it as a three-dimensional shape, it would look something like this now, right? And we're stacking squares on top of it. And so ultimately, it's going to look something like this. Oops, got a little carried away there. All right. Now, to integrate it and find that total volume of that three-dimensional shape, we're going from -6 to +6. And I get 102.4. All right, let's go ahead and move on to our next example problem. So up to this point, we've been stacking squares on top of these things, right? Well, we're going to change it to equilateral triangles now. All right. So before we begin the problem, let's talk about equilateral triangles a little bit. An equilateral triangle is a triangle with 3 equal sides, which we'll call S. Now, the formula for finding the area of an equilateral triangle is radical 3 over 4 S squared. That's how you find the area of an equilateral triangle. Okay? That's going to come in handy for knowing our next problem here. So, let me go ahead and clean that off real quick and get started. So the base of a solid is the region enclosed by the semicircle. So this is the base of my shape. The region enclosed by this shape and the x-axis. So once again, we're just going to the x-axis. So the distance between the curve and the x-axis is going to be the base of my shape. And that length right there is just the y value of this curve, which is y equals radical 49 minus x squared, and that's going to be my base. Now I'm going to show my steps here once again on this one. I didn't show it on example 2 because we kind of already knew the steps were pretty much the same. They're pretty much the same here too. It's just that the second step is going to look a little different. The way that you find the area of an equilateral triangle is by taking the base, and you're still going to square it. But the difference is now it's going to have a radical 3 over 4 in the front of it. That's how you find the area of an equilateral triangle. So when you're stacking equilateral triangles on top of it, that's what it looks like. Now, if I were to draw a three-dimensional picture, which once again, I would encourage you guys to try this. You don't have to. You could totally do these problems without doing this. But if you were to draw this as a three-dimensional shape, it's going to come out looking something like that. And if you stacked an equilateral triangle on top, it might look something like this, right? We're just stacking a whole bunch of equilateral triangles on top, right? And that's going to create a new shape for us, okay? A new volume. So if I wanted to find the area of this equilateral triangle, I'm going to do radical 3 over 4 times the base, which we know is the square root of 49 minus x squared squared. And we're going to integrate that once again from negative 7 to positive 7. So the only difference is the fact when you're doing triangles as opposed to squares is that it's going to have this radical 3 over 4 in the front, and that's really the only difference. And that's because that's how you find the area of an equilateral triangle. And when you add together all those areas, you get the volume. So once again, we can go ahead and punch this into our calculator. Here's how I would do it. I would call this y1. And then in my calculator, after I typed in y1, this is what I would type in on my home screen. Oops, not y to the first power, y1, that squared. So this is what I would type into my calculator. So I would enter this as y1, and then I would type that in. Now you could include this 3/4 in your y1, but the problem is you got to be careful. No, actually, I just wouldn't do that at all, because then when you type it and you square it, you're going to end up squaring this, and you don't want to do that. So if I were you, I would just leave the 3/4 out of it. Okay, so when you type in your y1, just put that in the y1 spot, and then when you go to your home screen, then put your 3/4 in. Okay, so this is what you'd get if you did it. And just a word to the wise, when you're doing this, you're also going to want to put your fraction here in parentheses when you type this into your calculator. Okay, so this is what you'd get, and you should end up with about 198.031 is what I get. All right, so we're going to do a student practice now. I'm going to have you guys do number 3 on the homework. You're also doing equilateral triangles. Now this time though, your setup's going to be a little bit different than mine, because I was just finding the area between a curve and the x-axis, so I just had one function. But for your guys' problem here, you're finding the area between this curve and this one, so you're going to have to do the y1 minus y2 thing again here, okay? So keep that in mind. So go ahead and pause the video here, and when you unpause it, you'll see the solution. Okay, and so here it is. The distance between y equals 1 and x squared over 4 is going to be the y1 function minus the y2 function. That's the distance between them. Take the absolute value just in case we got the order wrong. And that's going to represent the base of the equilateral triangles that we're stacking on top of it. So once again, that's going to look something like this. And where this is the bases. So this here would be the base of a equilateral triangle. And then we're going to stack it on top of there, right? And the base of that equilateral triangle is y1 minus y2. And if we square that, and multiply it by radical 3 over 4. That will tell me the area of that triangle. And then if we integrate from here, which is -2, to here, which is +2, we're going to add together an infinite number of these little triangles, and that will tell me the total area, which is 0.924. And as you're punching this into your calculator, once again, make sure that you put your radical 3 over 4 in parentheses. And then you have your square on there and all that good stuff. All right? All right, one more problem before we end this lesson. Let's go ahead and take a look at number 4. We're going to talk about rectangles now. Now, rectangles are a little bit different because you kind of have to get creative with this one. All right? It's not as, getting the base is not quite as obvious. All right. The base of a solid is the region enclosed by this semicircle here. So here's my base, and once again, I'm getting the easy one where it's just one curve. So this is my base. So let's label it as such. That's my base. 1 base equals the radical 25 minus x squared. Now, I'm going to be doing a rectangle. Now, the area of a rectangle, though, is base times height, right? Unlike a square, the base and the height are not the same. So let's go ahead and take a look at this a little bit more closely. I know what my base is. My base is the square root of 25 minus x squared. That's the base of my shape. So I'm going to go 3D with this now, right? It'll look something like this. And I'm stacking a rectangle on there. And there's the base of there's one of my bases of my rectangles, right? Which is just this y value. Now, with a rectangle, you have to know the height also. It's not as obvious. Now, here's what it tells us here. It says that for these rectangles, their height is half this base. Okay? So in other words, if the rectangle is this long, the height is maybe about half as much. And so the rectangle will look more like that. So now, if my base is this and the height is half as much, then I just have this. There. So that's base, there's height. So my height is half as much. So it's the same thing as the base, it's just half as much. And there you go. Now you can leave it like that if you want to. And then you can integrate. So we have this, which I'll just call y1, if you don't mind, times another y1, which is just y1 squared, and then a half in the front of it. Now, that's going to be the area of my rectangle, and if we integrate it from left to right, that's going to add together all those rectangles and give me the volume of the shape that would result from that. Okay? And so there you have it. So now you could type it in like this if you wanted to. I think, and don't forget, by the way, once again, you want your fraction in parentheses when you do this. But for me, I think I'm just going to keep it easy on myself. And instead of writing y1 times y1, I'm just going to put y1 squared. Okay, just because they happen to be the same. Sometimes, though, they might give you a new height, which is completely different. So you just got to get creative with it. In this case, it said it's half the base, so I just put half the base there. All right. So I'm going to go ahead and type that into my calculator, and we'll see what we get. And trying to type that in, I got an error because I got my limits wrong. We're not going from -7 to 7. It's -5 to +5. Oopsie doopsie. I'll go ahead and fix that right now. So I get 83.3 bar as the final volume of this three-dimensional. All right, let's go ahead and have you guys do one more homework problem. Have you guys do number 4, of course. Right? Now it looks pretty similar, actually, but you'll notice the height is different. The height is not half the base, but it's actually twice the base. So go ahead and see if you guys can figure out the answer to this one, and when you unpause the video, you'll see the solution. So the base is the distance from my curve to the x-axis, which is represented by the y value, which is given by the square root of 25 minus x squared, so that's my base. And that's the base of my rectangle. They tell me the height of my rectangle is the same thing as the base, it's just twice as much. So we have base, and then here's my height, twice the base. So if I call the base y1, then as I rewrite this, it'd be 2y1 squared, because you have the base being multiplied by itself. And then we're going from -5 to 5 once again, and you end up with a total volume of 333.3. Right? And that will end that one, and we'll do a couple more types of problems next time. But for today, that ends it. See you guys next time. Finish up the rest of your homework, and we'll see you in class.